Sorry, Prof, you're muted right now.
All right, let's start again. So correlation functions are the direct observables in any quantum mechanics, quantum field theoretic problem. So they're really, really important to know how to compute, etc. So when a theorist looks at a particular theory and computes things to go give to our experimentalist friends, the things that we compute are correlation functions, right? And in particular, 2, 3, 4-point correlators give us a lot of information about such physical systems. So today I want to start by setting up the machinery for correlation functions in quantum mechanics, and we'll see how, in the same way that we started off looking at the path integral in quantum mechanics, and then this really sets up, the same way we set up the problem of computing a path integral by computing a straightforward one-dimensional integral. This is going to be the analog. We're going to compute correlation functions in quantum mechanics, which are pretty straightforward to do. And then we're going to port this over to the quantum field theory of bosons and fermions a little later. But the heavy lifting, all the legwork we're doing now in this section. So it's important that you get to grips with this material at the basic level first before we go to anything more complicated. Any questions? Okay, so correlation functions are the direct observables in quantum mechanics and quantum field theory. These are the things that we want to know how to compute. So Nitin, for example, is an expert in computing what are called out-of-time order correlation functions in certain quantum mechanics problems, and this is going to be similar but not quite the same. So the kinds of correlation functions that are all the rage right now are what we call out-of-time order correlation functions. These things compute quantities in non-equilibrium settings. So we're going to be primarily concerned with equilibrium quantum mechanics or quantum field theory. And so we're going to compute what are called time-ordered correlation functions. So in quantum field theory, these time-ordered correlation functions take the following form. So I'm just going to write it out now. We're not really going to compute this right now. We're first going to start off by computing things, the analog in quantum mechanics, but it's worth stating where we're going. So in quantum field theory, these things are of the form the hat over the field variable here tells me that I'm looking at a field operator. And I'll expand on each of the, I'll expand on each of the elements of this just now. So these are of the form like this, where this here is a vacuum state of whatever theory we're looking at. These phi's are Heisenberg field operators. and the hat tells me that it's a Heisenberg, that it's an operator. And this T is what we call a time ordering instruction or time ordering operator. And what the time ordering operator does for us is the following. It orders fields by as follows. It takes the earliest fields and it puts them to the far right. So for example, and concretely, the time ordering operator on two fields phi at x1. By the way, this is a space-time variable x1, which means that it's got components x1 naught, x12, x11, x12, x13, etc. And x1 naught is traditionally defined to be the time component. So this guy is the instruction to write down the operator of, to write down the product of phi at x1, x2 as phi of x1, phi of x2, if x1, if the time component of x1 is bigger than the time component of x2, meaning that x2 takes place earlier, or it's phi of x2, x1, if the opposite is true. So if x2 takes place later than x1. Is that clear?
Yes.
Yes.
Okay. So this is how time ordering works. Okay, so typically when you see a correlation function like the thing on the left there, like this, with this T sitting in here, it's an instruction to order the field operators earliest first, meaning on the right, and then work your way leftwards from there. Okay, so this is what you would see typically in quantum field theory. In quantum mechanics, the corresponding objects are endpoint correlation functions. So endpoint correlation functions or correlators. And if you have some, statistics knowledge, this is precisely the same thing that you would compute when you compute correlation functions or correlators in statistics. Right? In quantum mechanics, are the functions of time, n-dimensional functions. Let's call them G, N, meaning we're talking about an endpoint correlation function. And I'm going to call them G for a good reason that's going to become apparent a little later. And G is an n-dimensional variable, sorry, n-dimensional function, meaning it takes n arguments, t1 through to tn. And I define this guy to be 0 time-ordered product of q of t1. Remember, in quantum mechanics, everything's just a function of a single variable. Through q of tn, where the q's are going to be the operators, the position operators corresponding to the position, the generalized position variable q, acting on O. Okay. So that's just a notation where I've replaced the position operators, which I was denoting by x, to q. It's nothing particularly deep about that. Right. But these are the kinds of operators, these are the kinds of functions that we want to compute now. Okay, what we would really like to do is develop a path integral for this correlator, right? So to develop a path integral for this correlator, we first need to write the path integral in terms of a Heisenberg representation, right? So I need to write down things in terms of Heisenberg operators. And there's a good reason for this that should become apparent just now. So let's start off by writing down Heisenberg operators associated to the Schrodinger operators Q. So in the Heisenberg picture, we have the following. We have that the operator Q of t is related to the Schrodinger operator Q by e to the I h t times Q times e to the minus I h t. Okay. And eigenstates of this operator, well, with states qt defined to be e to the I h t acting on the state q. Eigenstates of this operator satisfy the following. That q of t acting on this qt produces the eigenvalue, which I'm going to label by qt. Okay. The corresponding path integral or amplitude which we'll traditionally call K, is as usual what I get when I take the state Q, act on it, evolve it in time to some later time, capital T. Don't be confused by time ordering operator. And then project it into the final state Q prime. And this is what we would call Q prime at T projected onto Q of naught. And this is what we were denoting by the integral of over all paths Q of e to the I s. Okay. So let's do an example and see how to think about these correlation functions with time ordering operators and things in terms of path integrals. Okay. So to do this, I want to focus on one such path integral, and this is the 2-point function. So let's illustrate with the 2-point function. G with the 2-point function G 2 of T1 T2, which by our definition is Q prime T time ordered operator of Q of T1 Q of T2 Q at naught. Okay. What we want to do here is get an expression for this object as a path integral. Right? So to this end, I'm going to assume, so let's suppose that T1 is greater than T2, right? Meaning that T2 occurs first. So this is an assumption. I will come back and justify the assumption just now. So let's assume, for argument's sake, that T1 is greater than T2. If T1 is greater than T2, then I can immediately write that this is just Q prime T, Q of T1, Q of T2, Q of naught. Okay. And that's because of the time ordering operator, and we know how it acts. Nitin, you have a question?
Yeah, so sorry, didn't we define the endpoint correlators to be specifically related to the vacuum in the first line in this slide?
In the first line in the slide, I defined this as the object that we want to think about in quantum field theory. I'm still building up to that point.
Okay, got it.
All right, I will come to it. That's an important point to note, and we will talk about the vacuum, and we will talk about how to think about the correlators in terms of the vacuum just now. But okay, maybe I can make you feel better about this by doing the following. Let's drop this 2 here. So we're not quite talking about the same thing that I defined. Is that better?
Yes, it is.
Okay. So I just defined this object. I'm going to call it a 2-point function. It's going to be related to the 2-point function I want to consider, but it's not there. We're not there yet. Okay. So let's think about this thing. What is it exactly? Well, I know that I can express this particular object as follows. It's the integral, the path integral over Q of e to the is. So what I want to do is I want to expand this object by inserting resolutions of the identity. So I'm going to integrate. So let's start off by Q prime time T, Q of T1. Now I want to stick in a Q1 at T1, Q1 at T1, Q at T2, Q2 at T2, Q2 at T2, Q at naught, and because I'm resolving the identity here, I've got to integrate out over the intermediate Qs, Q1 and Q2. Okay, so again, all I've done is I've inserted identities. I've inserted an identity between Q1 and Q2 and Q2, Q at T2 and the initial state. Well, I know that these Q comma T's are eigenstates of the operator Q, which means that they're each going to act, each Q is going to act on its eigenstate. So then I'll get integral over Q1, integral over Q2, Q1, Q2, these are the eigenvalues, then an integral, a path integral from Q1, T1, to Q prime, T, integral over Q, e to the I, S, path integral from Q2 at T2 to Q1 at T1, keeping in mind that T1 takes place later than T2. dq e to the is, path integral from Q at naught to Q2 at T2 e to the is. And then I can compose these path integrals the same way that I can compose ordinary integrals and write this thing simply as the path integral from q of naught through to q prime at t dq q at t1, which is what I was calling q1, q at t2, which is what I was calling q2, e to the is as the common factor that I take out. This was true for t1 greater than t2, so I can write out the time-ordered operator in that way. As an exercise, I would like you to show that this result is completely unchanged if instead I had assumed that T2 was greater than T1. Well, the result of these two things together, in other words, the assumption that T1 is greater than T2, and you checking that it is unchanged for when T2 is greater than T1, tells me that the path integral automatically encodes the time ordering in the sense that the following is true. That Q prime T time ordered product of Q at T1, Q at T2, Q at naught is equal to the integral from Q at naught to Q prime at T dq Q at T1, Q at T2 e to the is. And you see that the Q sitting inside the path integral, we don't really care what their ordering is. But the Q sitting outside the path integral, on the left-hand side, these things have some necessary ordering. And the T, the time ordering there, orders this for us, but this particular ordering is automatically taken into account in the path integral for all times. So this is the key result here. And then it's kind of tied into the question that that Nitin asked a little earlier about the semi-classicality / classicality of the path integral, why things look classical. Or noticing that things kind of look classical. Like we're not actually talking about, you know, the kind of quantum mechanics things, the quantum field theoretic things that you would normally talk about in a course in quantum field theory or quantum mechanics. And there's a good reason for that. The reason for that is precisely this, that within the path integral, order doesn't matter. Whereas outside the path integral on the left-hand side, because these are operators, order does matter. Does that make sense? Nitin, does this give you a feel for why you know, when you work with path integrals, you can kind of still think classically?
Yeah, it does.
Okay, good. So now let's come to the other question that you raised, which is that I originally defined the endpoint correlator with regards to not any old states in the theory, but very particular states, vacuum states, right? And so typically what we do when we compute things in quantum field theory is we compute vacuum to vacuum amplitudes or vacuum to vacuum elements. And this starts by expanding these states that we have, Q prime T and Q of naught, in eigenstates of the Hamiltonian. And then if we evolve toward negative imaginary time, by the same arguments that we used earlier for statistical mechanics, we should expect that there too the ground state will dominate. In other words, we should be able to approximate So we want, or rather, we are interested in the following. In vacuum to vacuum, we're interested in vacuum to vacuum vacuum to vacuum amplitudes. Where we're going to approximate, I think I'll phrase this, okay, for which we're going to write 0 t, 0 minus t, which will approximate q prime t, q prime, sorry, q minus t, where I've symmetrized the interval. So instead of going from 0 to t, I go from 0 to 2t, and then I shift that from minus t to t. And this is what we would have as the path integral dq e to the is, or d little q e to the is. Yeah, okay, d little q e to the is, right? So then what we want to compute is the endpoint correlation function. So to compute the endpoint correlator, Gn of T1, T2 through Tn, which recall was this guy. What we do is we simply insert a corresponding set of insertions into the path integral. And so this here would be proportional to the integral d. Now I'm going to beg some patience with some abuse of notation here, just because it's going to serve a later purpose in how I do the integration. So normally I would define the path integral with respect to the small q's, which were eigenstates of, which were labeling the eigenstates of the operator capital Q. This is only because I want to distinguish between operators and variables, in which, you know, my notation for operators, I don't want to drag around I don't want to drag around hats everywhere. So I just use capital and small letters to make that distinction. And so here, I'm going to go back to the operator notation and just replace this with little q's. Actually, let me see if I need to. Yeah, okay. So I'm gonna replace the little q's with capital Q's, but it should be clear from the notation what it is I'm talking about. And if it's not, I can always try and explain a little better. Okay. So, but the point is, what we do is we insert some set of insertions into the path integral, and that's the thing that we want to compute. Now, I've put an approximately equal to sign here, or it's an approximately equal to sign. In fact, what I should do is put a proportional to sign. And I can turn this proportionality into an equality by some appropriate normalization. So in this case, what we're really interested in, and this is going to be our definition here, is the normalized endpoint function. And the normalized endpoint function is going to look like this. Right. So normalized endpoint function is what we're going to be computing. G n of T1 through Tn, which was this guy, 0 T Q T1 through Q Tn, 0, is equal to, or by our definition, 0 T time ordered product Q T1 through Q Tn, zero minus T. And I normalize by dividing this through by 0 T 0 minus T. Okay. And this is going to be precisely the path integral. Integral over states Q of T1 through Q of Tn, e to the is, divided by the path integral over Q of e to the is. And this is the quantity that we're going to try and work out how to compute. All right, so this is the thing that we're interested in. This is going to be the endpoint, the normalized endpoint function. Okay. To compute the numerator of this quantity, because the denominator of the quantity is easy enough to calculate, but to compute the numerator of the quantity, we're going to imitate what we did in the quantum mechanics case that we worked with previously and add a source term. So to this end, so to calculate this thing, to calculate this we imitate, or rather, let's just go straight to the punchline. We will add a source term. So what we want to do is consider the following function. So this is a definition, and I'll justify why I call it what I call it just now. So let's define the following function. Functional. I'm going to define a quantity I'm going to call Z, which is going to be a functional of the source function J, and it's going to be defined to be the path integral over Q of e to the I times S, the action, plus a source term, which is going to be an integral over T of J of T, Q of T. So some linear term in Q, as we did for the quantum mechanics case. And then I'm going to divide this through by the integral, sorry, I'm going to divide this through by the integral of e to the is integrated with respect to Q. Okay, and if you want to be neat about it, let me just move this thing down. So Z of J is defined to be this. Okay. I'm going to call this function a generating function, and you'll see why just now. Because what this guy does is it generates correlators for me. So I can start off, and if I know this quantity here, which the reason I use the Z, as you may suspect, is because it kind of is related to the partition function that we already encountered in the statistical mechanics. God damn it. Sorry, let's try that again. All right, so this Z is going to be related to the partition function that we've already encountered in statistical mechanics. And I'm going to call it, for our purposes, the generating function, because what it's going to do for us is it's going to generate correlation functions in the following way. So this is the generating function. So how is it the generating function? Well, let's see how this is related to correlators. And I want to start by acting on Z with a derivative. And in fact, the derivative I'm going to act with is a functional derivative, because I'm differentiating with respect to a function J, and I'm going to differentiate with respect to J at T1. Let's see what we get. Well, minus I is just 1 over I, so let's just drag that along for the ride. Delta by delta J at T1, that's what we're differentiating. And we want to differentiate Z of J, and as usual, we're going to turn the source off at the end of this. Okay, so this is if I functionally differentiate with respect to J, I pull down a factor of Q in the exponential, and then if I divide by, I pull down a factor of I times q. There's a delta function there as well, but that's what sets that's what sets t equal to t1. But this gives me then an integral with respect to q of q at t1 e to the I times s plus the integral with respect to t of jq. And then I want to normalize this by dividing through by the integral with respect to q e to the I s. And then at the end of the day, I want to set j equal to 0. Okay. Well, if I set j equal to 0 in the exponential in the numerator, that easily sets j equal to 0. So I get the integral with respect to q of q at t1 e to the I s, and I have to divide through by the integral with respect to q of e to the I s. And this is precisely the one-point function like that. So differentiating once with respect to j computes for us the one-point function 0, q of t1, 0. By first, so if we turn this around and ask, if we want to compute the one-point function, if we want to compute this one-point function, what do we need to do? Well, the answer is we need to compute the generating function, z of j, for some source j, differentiate it with respect to j, and then divide by a factor of I, and then set j equal to 0, and that'll give us the one-point function. And in fact, every time we differentiate j, we end up inserting some factor of q in the correlator. And so this gives us a way to compute endpoint correlation functions by extension as follows. So the endpoint function zero time ordered product q of t1 through q of tn can be computed then by working out 1 over I delta by delta j at t1, 1 over I delta by delta j of tn, all of this acting on z of j. And then once the dust is settled, you evaluate this thing at j equals 0. So there you have it. Here is an expression that will allow you to calculate then the endpoint correlation function. And just to go back to what I said earlier, this is really the name of the game. If you can calculate the endpoint correlation functions for all of the operators in some field theory that you're working with, you know everything that you need to know about the field theory, because these endpoint correlation functions are the observable quantities. These are the quantities you want to calculate in that field theory. Okay, and here you have it. If I know what the generating function z of j is, and again, this z of j is going to be related to the path integral, and it's going to be related to the partition function in a finite temperature field theory. If you know what this generating function is, just by differentiating the generating function repeatedly, you're computing the correlation functions. And you can calculate the correlation functions for any old operators in the theory that you want, just by inserting the appropriate insertions in the path integral. So it's a hell of a powerful thing, because once you know the generating function, you know everything that you need to know about the theory. Is that clear?
Yes.
Okay, so what we want to do next time, I'm going to stop here, but what we want to do next time is we're going to illustrate this idea going back to the quantum harmonic oscillator, and I'll show you how things change now when we deal with not a Euclidean oscillator, and we'll give some interpretation for how these things change, and we'll talk about the effective action that we can use to compute what I call connected correlation functions. All right.
I might have lost track of the argument here, but I just want to understand, like, we are going to the generating function because apparently it's easier to calculate the generating function than just plain old action and then integrate and everything.
In general, yes.
In general, so
yeah.
Like there must be cases where it's not so.
Correct. There are cases where it's not so. In fact, where you mean where it's not so easy to calculate where it's easier to calculate the endpoint correlation functions rather than the generating function?
Yeah.
Yes, there certainly is. In fact, in the simpler cases, in simpler problems, the quantum harmonic oscillator is going to be exactly one of those cases. It will be easier to calculate the endpoint correlation function directly than it will be to compute the generating function.
Okay, and to be honest, I simply don't get why would someone think it's easier to calculate a generating function. I mean, like, this is a technique, right? So
yes, but it's not necessarily that you're not necessarily shooting for easier. You're shooting for more understanding. And it turns out that knowing the structure of the generating function gives you more understanding about the quantum field theory than just computing endpoint correlation functions. It gives you more understanding about the structure of the theory. So, you have obviously heard of amplitude-hedrons, right?
Yeah.
Right. So then you know the story about amplitudes, okay? So amplitudes in the Arkani-Hammett sense of the word are related. The amplitudes are precisely these endpoint functions, okay?
Yeah.
And what you want is to understand, you give your amplitudes to your experimental friends and ask them to go off and measure things, and the things that they measure are the amplitudes. Yes?
Yeah.
But you get these things perturbatively.
Yes.
Okay. The generating function, in that sense, is the amplitude-hedron. The amplitude-hedron is the generating function for all of these amplitudes. They generate all of the amplitudes. So in some sense, they contain all of that information.
Okay.
So I'm not saying that it's necessarily easier or that you necessarily want it to be easier. What I am saying is that it contains all of this perturbative structure in this one non-perturbative thing.
Okay, got it. And another thing is like